All right, welcome everybody. Today we're going to talk about lesson number 48. And just to point out here, lesson number 48 and homework number 48 are actually the same. So you're going to fill in most of these examples together with me through the lesson, and then you're going to go back and see if you can try to fill in everything else. So this is all about graphing and analyzing the 6 trig functions. We did already see the graphs of the sine and cosine in a previous lesson, but we want to talk a little bit more in depth, not only about where they come from, but also about their properties. So if you think back to, the most common way for how you would graph something, especially something that you weren't terribly familiar with, you would go ahead and start by making a table of values, which is actually what I've done for you here. Just to be clear where those values came from, they came right here from the unit circle. Remember, if you wanted to graph the sine function, you would go around starting at 0, and you would graph all of the y values. Then if you wanted to graph the cosine, you would go around and graph all of the x values. The tangent would be the y over the x value, and then so on and so forth down the line. Keep in mind that you could actually graph lots of other values, not just these unit circle ones, but since these are the ones that we're the most familiar with, those are the ones we're going to kind of use to get us started. So going back to the lesson and the homework right here, notice that you have the 6 trig functions, and then notice that there is a little bit of a relationship. So remember that the sine and the cosecant, those are reciprocals. So you might want to compare the first column to the last column. Same thing with cosines and secants. You might want to compare those 2 columns, and then your tangents and your cotangents. A couple of other things to point out here. Notice that there's a little key at the bottom here that says anywhere that you see those 3 dashes, that's undefined. So what would it mean on the graph if something was undefined? We're going to check that out in just a minute. Then something else to point out here, anything that I'm going to highlight in pink, those are your quadrantals. Remember, at the exact top, left, bottom, or right of the circle. And then notice that everything else is by quadrant. So these are all your quadrant 1 values. And notice, of course, that everything is positive. These are all your quadrant 2 values, your quadrant 3 values, and your quadrant 4 values. So everything about the all students take calculus in terms of where things have to be positive and negative, that has to still be true in our table, and it has to still be true in our graph. So again, we already saw the sine and the cosine, but we're going to go through a little bit more particularly now to make sure that we understand completely where that came from. So let's go ahead and start by looking at the sine wave. If I was going to graph the sine wave, I would essentially go through this sine column, and I would graph the y values at each of those locations, which again, I've listed here for you in the table. So again, just to reiterate, let's say you start at 0. The y value at 0 is 0, hence the point 0, 0. Then notice we didn't really use the pi over 6, the pi over 4, or the pi over 3, but we could. So at 30, you're at a half. Then root 2 over 2 is a little bit larger. Root 3 over 2 is a little bit larger still. And then eventually, by the time you get to pi over 2, you're all the way up to 1. Notice that because sine's first quadrant, everything is positive. Then you're back to radical 3 over 2, back to root 2 over 2, back to a half, and then at pi, the y value is 0. Again, notice that's quadrant 1 and quadrant 2, and of course, everything is positive. Then you could start to now graph those negative values, and again, you could graph all of the values in between, but it turns out that if you focus on the quadrantals, that's really enough to kind of get you started. So these big green dots, those are going to kind of be the most important pieces. Those are the ones we're going to focus on as we start stretching and shrinking and moving the graph around tomorrow. Remember that you're taking the sine of an angle, so you could continue going around the unit circle as many times as you want in the positive direction or in the negative direction. So what I've just shown you there is just one cycle. You can then see over here to the left, here's a second cycle, which is what you would get if you were to go clockwise around the unit circle. And then every time you go through a value of 2 pi, you're going to go ahead and get the same exact picture. So a couple of definitions I want to remind you of and add in here, and there is a little bit of white space for us to do so. So the first thing you're going to do in the white space at the bottom of this page, you're going to go ahead and write for me the definition of what it means to be a periodic function, because all of these are. So again, periodic is kind of the most important part there. So a function is periodic if there exists a real or a positive real number C such that f of t plus c is equal to f of t. So again, this is the formal definition of what it means to be periodic. And it basically means if from wherever you start, you can go through a set value and then get back to the same exact value, that's what it means to be periodic. Then an offshoot of that is the period. So what does it actually mean to be a period? That is how long it takes a function to repeat. So repeat, periodic, hopefully it makes sense that that stuff all kind of goes together. Then there's a second piece of information I'd like to remind you of, and that's the difference between something being odd and being even. So you might want to go ahead and write this at the bottom of the back page where there's some space. So to remind you what it means to be an odd function, it means two things. First, it means that the graph has to have origin symmetry. What it means algebraically is that if you find f of a negative value, it's going to be equal to the opposite of whatever the original value is. We're going to focus mostly on the symmetry part, but it is good to know also a reminder of the algebra. Then, of course, if you're not an odd function, you're going to be an even function. Hopefully you remember that an even function has y-axis symmetry. And what it means algebraically is if you find f of a negative value, you should wind up getting the same value as if you were to take that positive value. So again, that's a reminder of stuff from earlier. So hopefully that makes sense. So now that we've reviewed what it means to be odd and even, let's go ahead and go back up here to the sine graph. The sine one is kind of the friendliest graph, so it's a good one to start with. One final thing that I want you to write to remind yourself of, we are going to use the value of n to represent any integer. So whenever you see me use an n, that means that you could go once around or twice around or -1 or -2. So n is going to stand for any integer. So now that we understand where the sine wave comes from, we want to be able to do an analysis of it in terms of the following. So starting with domain, you are taking the sine of an angle. And again, because you can go around the circle as many times as you want, the domain is going to be all real numbers. Hopefully you also remember that when you're on the unit circle, the length of the radius is 1 unit. That means that the highest value of the range is going to be up here at 1, and the lowest value of the range is going to be down here at -1. It includes those values, so we're going to go ahead and use brackets. As I mentioned below, the definition of a period is how long it takes to repeat. So highlighted in yellow, that's one full cycle of the sine wave. Then with the dots in green, that's a second cycle. So how long does it take for the graph to repeat? Well, you have to go one full trip around the circle, which means you have to go the full 2 pi. Then when it comes to x-intercepts, you don't just want to list them between 0 and 2 pi or between 0 and 4 pi. You want to list all the x-intercepts that exist forever. So if you take a look here, notice there's an x-intercept at 0 and at pi and at 2 pi, then again at -pi and -2 pi. So they basically exist in integer values of pi. So we're going to say x equals n pi. And again, remember, n is going to stand for an integer. So 0 pi, 1 pi, 2 pi, 100 pi. Any integer value of pi, you're going to have an x-intercept. When it comes to the y-intercept, there can only ever be 1 at most. So in this case, it's 0, 0. In terms of being odd or even, the easiest way from the graph to check is having to do with the symmetry. So this is an example of a graph that has origin symmetry. Remember, origin symmetry means if you were to take part of the graph and you reflected it over the x, and then over the y, it should match up exactly. So these two pink pieces match up, the unhighlighted parts would match up, which means this is in fact an odd function. If you're looking to understand it algebraically, what it means to be odd is that if you found f of pi over 2, and if you found f of negative pi over 2, those y values should be exact opposites, which again, hopefully you would agree that that's also the case. Then finally, for increasing and decreasing, you're just going to tell me from 0 to 2 pi, and notice that there are parentheses because you always use parentheses for all increasing and decreasing. I'm just going to go ahead and go from left to right. So starting at 0, I'm going to go ahead and be increasing all the way up from 0 to pi over 2. Then I'm going to be decreasing between pi over 2 and 3 pi over 2. And then I'm going to be increasing again from 3 pi over 2 to 2 pi. So I'm going to go ahead and add that over here. So again, x-intercepts, I want you to tell me for the entire length of the function in perpetuity, where increasing and decreasing, I just want you to tell me from 0 to 2 pi. So the way that we did the analysis of the sine wave is going to be very similar to how you do the analysis of the cosine wave. So you're going to do that on your own, but we're going to go ahead now and talk about the cosecant. So first of all, just as a reminder, the sine and the cosecant are reciprocals, which means you're basically taking the sine graph and flipping it inside out. Let's go ahead and take a look at the cosecant column. So again, notice it follows the same positive in quadrants 1 and 2, and then negative in quadrants 3 and 4. The thing we want to be most mindful of here is where the function is undefined. Notice that the function is undefined basically at any multiple of pi. So what does it mean graphically if the function is undefined? Well, that means there's going to be asymptotes there. So it's a little bit difficult for you to see them. So you're going to want to go ahead and add in everywhere it looks like the graph is kind of shooting all the way up or all the way down. Those are your asymptotes. So you might want to go ahead and draw those in. Certainly, in a case like this, if you are trying to talk about the domain, the fact that there are those asymptotes for sure means that your domain is not all the real numbers. So your domain is basically everything except for those asymptotes. So there's no way to write that in interval notation. So we're going to write it as follows. Instead of saying what x is, we're going to say what x isn't. So we're going to say that x cannot equal any multiple of pi. And how do we say that? Well, we're going to say cannot equal n pi. Basically, everywhere that there was an x-intercept, there's going to be a domain restriction for the reciprocal because that's where you're going to do 1 over 0. The range, luckily, we can just look at it. We can see that the range is going all the way down to negative infinity, then up to negative 1 with a bracket, and then picks up again at positive 1 all the way up to infinity. And again, just to be clear, this is a negative 1. And then the period is again how long it takes to go through one full cycle. And in this case, you have to include one full up-down motion. So in order to include the entire up-down motion, this again also has a period of 2 pi. And just so you know, reciprocals always have to have the same period, which these are. Then notice for the x-intercepts, it does not appear to ever cross the x-axis, which sad but true, there are none. There is also no y-intercept. In terms of being odd or even, again, there is origin symmetry. So this is odd. And again, when you compare reciprocals, if one is odd, the other has to be odd. If one is even, the other has to be even. And then finally, the increasing and decreasing. I'm just going to give myself a little bit more space here. So starting at 0, you are decreasing from 0 to pi over 2. Then you are increasing from pi over 2 to pi. Then you're increasing again from pi to 3 pi over 2. And then you're decreasing again from 3 pi over 2 to 2 pi. And just in case you're wondering, why do you have to break this up? You always have to break for asymptotes. So anytime there is an asymptote, there's a break either in your increasing or your decreasing or your domain or your range. That just kind of has to be the case. So you're going to go back and try to do the cosine and the secant on your own. Those are, again, reciprocals. See if you can understand where the graph itself comes from. See if you can analyze it first with the cosine and then with the secant. You're going to try to fill all those in, and then you'll go back and check your answers. And then for the tangent and the cotangent, we're going to do just one of them, and then you'll go back and try to do the other one. So we're going to go ahead and look at the tangent. So again, when it comes to the tangent, you would go back and look at the table above. You would go around and calculate the y values over the x values, and those would give you all of the tangents. Starting at 0, the tangent of 0, that would be 0 over 1, which would be 0. You're also going to get a 0 at pi and at 2 pi, and then so on and so forth in multiples of pi. Whenever you get to the top of the circle or the bottom of the circle, you're going to wind up dividing by 0. Division by 0 is not possible. That's going to give you an undefined. So again, that's where your asymptotes come in. So anywhere where it appears as though the graph is shooting off to infinity, those are, of course, your asymptotes, which you might want to draw in a little bit more precisely. So let's go through and take a look at the analysis here. So before we do that, again, just pay attention to the positivity and the negativity. Remember that tangents are supposed to be positive in quadrants 1 and quadrants 3, and they're supposed to be negative in quadrants 2 and 4. So all that, analysis we've done along the way, that is all still true. When it comes to domain, we certainly cannot have anything that has an asymptote. Notice it's a little bit more difficult than in the past. It's not every multiple of pi, and it's also not every multiple of pi over 2. It's only starting at pi over 2, and then you have to go pi units to the right or pi units to the left in order to get all the other asymptotes. So again, instead of saying where the domain is, we're going to say where the domain isn't, and we're going to say x cannot equal pi over 2 plus n pi. And what that means is that if you start at pi over 2 and you keep adding positive pi's to the right, or you keep subtracting pi's to the left, you're ultimately going to hit all of the asymptotes. For the range, it appears to go all the way up and all the way down, so that is an all real number situation. Little bit of a difference here for the period. So remember, the period is how long it takes to go through one full cycle. And in terms of the tangent, one full cycle is one complete up-down motion. So you don't actually need to go all the way around the circle in order to get one full motion. You only need to go halfway. So you only need to go pi in order to get it. So the period of the tangent is only pi because it repeats every pi units instead of every 2 pi units. For your x-intercepts, again, I want to know where literally all of them are. So all of these x-intercepts, notice that they are located at integer values of pi. So I'm going to say x equals n pi. And just so you know, n pi and pi n, those are the same. Y-intercept, only 1, 0, 0. This is, again, an example of a graph that is odd because it has origin symmetry. Here's your values from the first quadrant, which if I reflected it over the x and then over the y, it would match up exactly. And then finally, increasing and decreasing. So notice that it's increasing from 0 to pi over 2. And then it's actually increasing again from pi over 2 to 3 pi over 2, but we have to take a break because of that asymptote. And then it's actually increasing again from 3 pi over 2 to 2 pi. So the tangent graph actually increases the entire time, but you just have to break it up because of the asymptotes. So using what I showed you there in that analysis, you're now going to try to see if you can analyze the cotangent in a similar fashion. So again, just to reiterate, this worksheet here is both lesson and homework. You're going to go back now and try to fill in everything that we missed, and then you'll go back and check your answers to homework 48, and then obviously compare it. When I see you next time in class, we will start by going over these and answering any of your questions. And then we're going to talk about what happens as we start making changes. What if we want to stretch it, or shrink it, or reflect it? So all that stuff is going to be coming up tomorrow. So thanks very much for tuning in, guys. Go back and fill in all the blanks, check your answers, and we will catch you next time.